Hello everybody. Today we shall discuss about some application of the rigid body mechanics that we have learned. I'll talk to you about three cases, and all these three cases we actually see in, you can observe them in real life. And I will work out one case. One I will give you as an exercise to do as a homework, and the other you can at least look at the problem, and if you wish, you can try to solve them. Okay, so let me first describe to you what are these three cases. The first case is motion of a symmetric top. This is the one that we'll work out in detail. So what is a symmetric top? A symmetric top looks something like this. So it's symmetric about one axis. So I can call that z axis, and then you have x and y. We'll look at the motion of such a symmetric top with one point fixed. So this is the fixed point. Now you will agree that I can have three principal axes for this system, and those three axes can be called as or the moment of inertia along these three axes can be called as Ixx, Iyy, and Izz. So these are the symmetry axes of the system, and Ixs and Iyy will be same because of the symmetry, and we will call that I alpha. And Izz definitely will be different. We'll call that I beta. This is just a choice that we make. There is nothing sacrosanct about calling why we call them I alpha and I beta. Ixs and Iyy are same, so that's why we call them I alpha, and the other one we call I beta. Okay, so that is a symmetric top, and we ask the question that what happens if I consider the motion of this top with one point, which is the point here, that is fixed. So that is one question that we will ask. So that we'll do in detail, so we'll come back to it later. Next is something that I will ask you to work out. We have all seen bicycle. I can take that as granted, but there is something called unicycle. The question is that how an unicycle steers. Okay, so that is something that I keep you as an exercise. So let me draw first how the unicycle looks like. Unicycle is, as you can imagine, has a single wheel. It's a wheel just like the wheel of a bicycle, so you can expect spokes like this. There is something very interesting about bicycle spokes. We can discuss about that if you have some time, at some point. Okay, now let me use some other color. Here is the hub, and okay, so obviously there's a rim and there is a tire, which I have not drawn. Usually you have a paddle here and a paddle in the other side, which I am not drawing again. And then from the hub, and you can imagine that it's also there in the other side, comes up this fork. On top of the fork you have the seat. So somehow you balance and ride this. And believe me, there is at least two people I know of who have gone around the world using a unicycle. So it's quite rideable. Okay. Now the question is the following. Question is that this cycle is turning in a circular arc of radius RT. So turning radius. So that's why I call it RT. Okay, so this is the origin say. So it's going around this, which means if I look at the instantaneous position of the wheel, it looks something like that. So the wheel has a spin, and the spin is constant in the arc. The magnitude of the spin is constant. It's better be, even for a cycle, if you try to change the spin while you are on the arc, it will be really tough to maintain the balance. I said it is being steered, which means you see that the direction of motion of this wheel will change, which essentially means that there will be a rotation along that axis. So let's assume the wheel radius is smaller, which is obviously a fixed quantity. Mass of the cycle is small m, and you can imagine there will be a rider on the top of the cycle. The rider will be sitting like this, and the mass of the rider is say capital M. So these are the parameters given to you to work out this example. Now, though I have drawn it like this, but if I see it from the side, then the cycle actually has to lean to turn. And this angle, let us call it theta. So this is leaning angle. If you have ever driven a bicycle, at least you know that that is how you turn. So you have to figure out, given all these things, how does such an unicycle steer? And that will give you essentially a relation of the leaning angle theta with respect to all the other quantities that I have given you. So what angle should you lean such that we should be able to make the turn with that turning radius. Okay, so this is a problem that I give you as a homework. And the third problem, which if you wish you can work out, but I will not insist you to do as a homework, is called a tennis racket theorem. It has many other names also, but it is something very interesting. So let me tell you. The tennis racket looks like this. It will work with the badminton racket also, I guess. The tennis racket looks like this. Most of the mass is there in the ring, and then you have some woven. Okay. Now say you are holding the racket here, and you give a jerk such that when you release the racket goes up with a toss. So you give a spin like this, give motion like this in the racket, and you let it fall down. What you will observe is, if I draw the racket now, just like a physicist will draw a racket like this, and remember that you have given it a turn like that. What you will observe is it not only turns like this, it also would have turned like that. And there is a particular reason why it happens, and I'm not going to tell you why it happens, but it's called a tennis racket theorem. Okay, so this is a problem that I at least will like you to look at. So there will be enough examples in YouTube as well. I would like you to look at the phenomena, and then if you are enthusiastic enough, you can try to solve for it using the rigid body mechanics that you have learned so far. Okay, so let us discuss the motion of the symmetric top. Now, even before we start that, I would like to remind you a few things. First of all, let me remind you of Chase's theorem, which basically told you that motion of a rigid body translation of a point preferably in the body. Most of the time we take as center of mass, but we may not also, plus rotation about that point. And Euler's theorem told us that motion of a rigid body with one point fixed only one rotation about axis, or I can think of three rotation. Right? These three rotations, we have been denoting them as three angles phi, theta, and psi. So which means for our problem, which is the motion of a symmetric top with the tip of the top fixed, we can write the Lagrangian L, which is t minus v, but I can just write L as a function of phi, theta, psi, phi dot theta dot psi dot. We will be working with a conservative system, so there is no time dependence in the Lagrangian. And you see that I have just written down the Lagrangian, which means I'm trying to get or use the Lagrangian approach, which will be very interesting because that's what we have learned for the entire course. Now we are applying it to a fairly complicated problem, which is the problem of the motion of a symmetric top with one point fixed. I'd like to remind you the idea of cyclic coordinates. And let me go ahead in time a little bit and say if the Lagrangian, the above Lagrangian, is not a function of phi and psi explicitly, then we will get p phi equals to constant, some constant, and we will also get p psi equals constant. This we have seen already. So the coordinates phi and psi are cyclic in this particular case example. And if that is true, then we can define a reduced Lagrangian. This is using Routh's prescription, if you remember. If I call it L prime, that will be our original L minus the constant momentum times phi dot minus constant momentum times psi dot. When phi dot and psi dot has to be written in terms of p phi and p psi. Right, so that will be our reduced Lagrangian. What will it be a function of? Remember now, L prime cannot be a function of phi and psi, and phi dot and psi dot is replaced in terms of p phi and p psi, so it cannot be a function of those also. So this is a function of theta and theta dot only. And then the third thing that I would like you to remember is that we have introduced Bartholomew identity, which essentially told you that because Lagrangian is not time dependent, I can define a constant of motion which, as I said, will eventually turn out to be energy. So I'm just writing that as energy for the time being, and this will be nothing but p theta dot minus L prime. Now, we will be using all these ideas in our calculation today. It will turn out that our Lagrangian is independent of the coordinates phi and psi, which you will see explicitly how it turns out. But it will turn out like that. So because of that, we will be able to write down a reduced Lagrangian of this form. And then we'll get this. And if you remember, what will eventually happen is that I will get E in terms of some kinetic term plus some effective potential. And it is that effective potential, if we analyze, we'll be able to know about the system. So that's the setup that we are trying to use. Is the exact same setup that we have already used. When did you use it? When you studied the central force problem. Okay, so let us start. Now this drawing that I'm going to do is going to be fairly complicated. So let me first keep a few things here. I will use these coordinates as my space setup axis. So let me draw my space setup axis. Capital X, capital Y, capital Z. So let me use small x, small y and small z for the axis which is fixed to the body. And remember, we called Ixx, obviously these axes which are fixed to the body we will choose as the symmetry axis or the principal axis. So these we called I alpha, and IZZ we called I beta. So the angular momentum omega, I can write it in terms of my body set of axis as omega x cap. I'm sorry, omega is the instantaneous angular velocity, not the angular momentum. So these are instantaneous directions of the body, and x cap, y cap and z cap are the instantaneous directions, and omega s, omega y, omega z are the components of the angular momentum along the body set of axis. If I know them, and if I know the moment of inertia, principal moment of inertia, then obviously my kinetic energy will be half I alpha omega x square plus half I alpha omega y square plus I beta, half I beta that is, Need a little bit of space. Okay, so that I understand that if I know omega x, omega y, and omega z, I can immediately write down what is the kinetic energy. Okay, so let's try to figure out what is omega x, omega y, and omega z. Now, what is the orientation? What is such an instantaneous orientation of the body of the symmetric top? Well, I can say that the symmetric top z axis is along this line. So this is z, small z. And I can draw a perpendicular from that into this plane, and this angle I call psi. Okay, this angle I call psi. The two z axis also makes an angle in between them. That angle I give a name. I call this angle theta. Okay, now let us first look at these two. This psi will change with time as this z axis is the position, instantaneous position of the system. So this direction is the instantaneous position of the system. Obviously it will change with time. So as that change with time, both psi and theta will change. Now change in theta I can write in terms of theta dot change in change in psi, I can write psi dot. And now if I actually draw the symmetric top like this, then there is a plane which is parallel to the small x small y plane, and I am drawing that parallel plane over here on the top of the top. Here is my small x axis and small y axis will go somewhere there. Okay, see, these small x and small y axis I should have drawn at the origin, but it will make things complicated, so I have drawn them there. And if I have a bead here, any point here, there can be a rotation with respect to that point. So let me choose a different color now. So I'm running out of colors, I guess. This motion corresponds to the spin of the body. So this angle I call phi. So change in phi I call phi dot. Okay, so let me move this a little bit downwards here, because you see this motion of phi, change of phi, is just the spin of the body. So this angle is called spin angle. Now this spin axis goes around the capital Z axis, the space capital Z axis, and that motion is given by psi. So that psi motion is called precession. Okay, change along theta is called rotation, change along psi is called precession, change in phi is the spin. Now these three angles are not very complicated angles. These angles, this type of angles we have already seen. So let me make a connection now with what you have already seen with what we are talking about here. See, the first rotation that we are talking about is along the body Z axis. So this is small z, which we call phi. If the body axis are like that, so then there is a perpendicular plane where the x and y axis of the body resides. And for the sake of understanding, let me draw the body like the following. So x is smallest, y is the largest, and z is the third largest. In the z direction, the extension of the body is third largest. Now this is, in this case, what will happen is, if I give a rotation along z, what will happen to my body is that the y-axis and the x-axis of the body can change. So it may become like this. Now my x is along this direction, y is along this direction, z remains as in the original direction. So this is a rotation in phi. Now let us consider a rotation which will make the z-axis vertical. So that will have the z-axis like this. Now it's a rotation about x. So x remains as it is. And the body looks so that's a rotation of theta, because you see that's the rotation that makes small z along the vertical. And then now I can do the psi rotation, which will orient my x-axis differently. So xy will become like this, x will become like this, z remains as it is. So that's the rotation about rotation about z, which is now along the body z axis, and my x and y also becomes the body x and body y axis. So you see, these three angles that we looked at are nothing but the Euler angles that we have discussed many times now. Okay, so what we have to do? Well, we have three instantaneous rotations, and accordingly I can write omega theta as theta dot, or modulus of omega theta as theta dot. What is the direction? It is along capital X. You see, omega theta is along capital X. Omega psi modulus is psi dot, and omega phi modulus is phi dot, right? So what all we have to do is to find the x, y and z component of each of these three omegas. So let us do that. Let us just write down these components. Omega phi is along this, which is along the body z axis. So both this x and body y components are 0. So this is 0. Omega phi dot y cap is 0. Omega phi dot z cap is phi dot. So phi dot is completely along z. Okay, so what we have done is we have written down all the components now. So omega psi, I have taken projection along x. Obviously that is psi dot, and let's see how you get the projection along x here. So omega psi, first let us see projection along z. Projection along z will be obviously omega psi, and which is psi dot magnitude, and z projection is cos of theta. If I go to x and y projection, that will be, instead of cos theta, that will be sin theta, and then I have to take sin psi and cos psi for x and y components, and that's what I have done here. So z projection is psi dot cos theta, and for x and y components I have taken the corresponding phi projections. So first theta projection, sin theta, and then corresponding phi projection. Similarly, you can look at what will happen for the 3 omega theta projections. So that's how I get all these components, and then I can write them down, clubbing the components of x together, which gives me omega x, components of y together, which gives me omega y, and components of z together, which gives me omega z. Okay, so what I have done now is I have written down omega, which is the total instantaneous angular velocity, in its component along the symmetry axis, where I can write down my ix's, iyy, izz in terms of psi dot, theta dot, and phi dot, and their cosines and sines. So I can write down the kinetic energy now, which, if you remember, was half I alpha omega x squared plus omega y squared plus half I beta omega z squared. We called izz as I beta, and ixx and iyy both we called I alpha. Now if I add omega x squared plus omega y squared, you see what happens. So first let us look at components of psi dot. So I get psi dot square, sine square theta sine square phi from omega x, and sine square theta cos square phi from omega y. Sine square phi plus cos square phi adds up to 1. So I get psi dot square sine square theta, which I have written here. Similarly, for theta dot square, cos square phi and sine square phi adds up to 1, I get this. And when I look at the cross term, I have psi dot theta dot sine theta sine phi cos phi here. I got psi dot theta dot sine phi cos phi here, and then with a minus sign. So they cancel out. And for omega z, I just write the omega z square. Now that is the kinetic energy. What is the potential energy? Well, it's easy to set up the potential energy here, because the potential energy is just because of gravity. And if I consider the distance to the center of mass to be L, which is this distance, then the potential energy and the mass of this object is L, m. Then the potential energy is simply mg L. I had written capital M, so let me change this to capital M, cos theta. So you can write down the Lagrangian, which is half I alpha psi dot square sine square theta plus theta dot square plus half I beta phi dot plus psi dot cos theta whole square minus potential energy mgl cos theta. What do you see? Immediately, as we promised, L is cyclic. There is no explicit psi dependence, no explicit phi dependence. So I can immediately write P phi, which is a constant. And what is P phi? P phi is I beta this I write as I beta times beta. It's a constant, so beta is a constant. Similarly, P psi is also constant. So what is P psi? P psi has contribution from both the terms. So P psi is del L. Remember that P phi is del L del phi. So I forgot to write that down. Let me write it here. Del L del phi dot, and P psi is del L del psi dot. Right? So what is P psi? Del L del psi dot. So I get a contribution from this term, which is, see, I alpha. Obviously, when I do the derivatives, there is psi dot square, so that will give me 2, which will cancel that half. And then, so I can just write I alpha there. So I get I alpha sine square theta from here. Psi dot, I'm not writing it as if till now. When I do this differentiation, I will get I beta, and then I will get another psi dot cos square theta. So let me write that here. So this entire thing is times psi dot. But I have another term which with phi dot also, and that term is I beta phi dot cos theta. Right? This I call I alpha times alpha. So alpha is also constant. So what I do now is I have these two equations of phi dot and psi dot. So one is psi dot times I alpha sine square theta plus I beta cos square theta plus phi dot times I beta cos theta equals I alpha times alpha. The other equation is again psi dot beta, I beta can be cancelled from both sides. So this is psi dot cos theta plus phi dot equals I beta beta. So two equations in phi dot and psi dot I can solve for phi dot and psi dot. So if you solve for phi dot and psi dot, it is straightforward. So I'm not doing it here. I have written down the solutions. So psi dot will come out to be I alpha times alpha minus I beta times beta into cos theta by I alpha sine square theta. Phi dot is a little complicated, but it also has in the denominator I alpha sine square theta. Here I have enter things times beta minus I alpha cos theta times alpha. So this is psi dot and phi dot. Now let me remind you something. So remember that when we looked over the reminders, I can now define an effective or reduced Lagrangian, which is L minus P phi phi dot and P psi psi dot, with phi dot and psi dot has to be written in terms of P phi and P psi, right? So let us try to do that. So psi dot and phi dot we have written in terms of P phi and P psi already. So let us calculate, because this will be easier to calculate to start with. Let us calculate P phi phi dot plus P psi psi dot times I alpha sine square theta. So what is this? P phi is I beta times beta. So this is I beta times beta times the numerator in phi dot, which is I alpha sine square theta Okay, so this is the first term. The second term is P psi is I alpha times alpha, and here I have I alpha alpha, so I get I alpha alpha square minus I alpha alpha times I beta beta, so that gives me I alpha I beta alpha beta cos theta, which is exactly this term. These two terms are same. So what do I get? So I get If I now try to write p phi dot plus p psi dot, this is nothing but now this entire thing times I alpha sine square theta, divided by I alpha sine square theta. So the first term, which also have I alpha sine square theta inside, just becomes I alpha I beta beta square. Remember that this is a constant. I alpha is a constant, I beta is a constant, beta we define to be a constant. What else do I have? I have something divided by I alpha sine square theta. This division is coming because this is what will come in the denominator in the right hand side now. Now what is this something? So let us have a look. This something has this term, which is I beta square cos square theta. This term, which is I alpha square, and combining the rest two terms is 2I alpha into I beta cos theta. So that's a perfect square. So I get p phi dot plus p psi dot as I alpha I beta square plus I alpha sine square theta in the denominator, and here I get I alpha times alpha minus I beta times beta times cos theta whole square. Okay, so that is going to be an important result that we will need shortly. Now before proceeding, remember our Lagrangian had things in terms of phi dot square and psi dot square. So in our Lagrangian was, apart from a factor of half, I beta psi dot cos theta plus phi dot square plus I alpha sine square theta psi dot square. Now here also I need to replace all phi dot, psi dot, etc. Lagrangian also had another term which let me write down here. Theta dot square. But this term we are not looking at right now. We are only looking at these two terms. What is that equals to? Well, just let us do the calculation. So it is I beta cos square theta psi dot square plus I alpha, let me write that here, sine square theta psi dot square plus I beta phi dot square, which is coming from that term, plus 2 I beta cos theta psi dot phi dot, right? What we want to do is, we want to write this in terms of p phi phi dot and p psi psi dot. If I can do that, then immediately I can use the right hand side here, which is independent of all phi dot and psi dot. Okay, so this is just a mathematical trick that you are trying to use. How can I do that? Well, let's do the following. P phi, p psi psi dot, right? So let me take psi dot common from this term and this term. So what I get is I beta cos square theta plus I alpha sin square theta. One psi dot I have taken, the other psi dot remains. Now let's look at this term, I beta cos square theta plus I alpha sin square theta times psi dot. If you come back here, so that is this term. I have to subtract an I alpha cos theta, I alpha alpha cos theta from here. Well, that is available Okay, so let us look at p phi. P psi. P psi is that term I alpha sin square theta plus I beta cos square theta psi dot, and then I have to add to it I beta cos theta phi dot, and that is available here. So I can just take one of this out of two, I beta cos theta phi dot, so that this entire thing and then is p psi. And what else do I have? If I take now phi dot common, this term gives me I beta phi dot, and the rest one of from the here gives me I beta cos theta psi dot. So I beta phi dot plus I beta cos theta psi dot. What is that? I beta phi dot plus I beta cos theta psi dot. So that is p phi. So this thing is p phi. So you realize that this entire thing is nothing but p phi phi dot plus p psi psi dot. So let us now try to look at what happened to our Lagrangian. Our Lagrangian, the original Lagrangian, was half I alpha theta dot square plus half, well, whatever is there with this half is essentially p phi phi dot and p psi psi dot minus mg L cos theta. So now I can write L prime quite easily, because L prime is nothing but L minus p phi phi dot minus p psi psi dot, which is simply half I alpha theta dot square. You see, I take out full of these, half of these were already here, so what remains is the half with a minus sign. So I write this minus m g l cos theta plus half p phi dot plus half p psi dot. Which I can write now explicitly in terms of or eliminating phi dot and psi dot. Because p phi dot and p psi dot we have calculated here already. So what is this? This has this term which is constant, and Lagrangian does not care about a constant term, so I can just throw it away. What all remain is I alpha minus I beta cos theta whole square by I alpha sin square theta. So 2I alpha sin square theta. This 2 is coming from the half, and the numerator I have I alpha minus I beta cos theta whole square. So that is my reduced Lagrangian, which is now only a function of theta and theta dot. And what we call this? This is the V effective as a function of theta. So as we already know now, I can use Bernoulli identity, and I can write a constant which is happen to be the total energy, which is I alpha theta dot square plus V effective theta. Where what is V effective theta? Well, it has two terms, mgl cos theta, which is the original potential, plus the excess theta dependent term coming in the effective potential. So after all these, the equation rather looks quite simple. And you know the rest of the drill quite well. We can now look at the problem in terms of V effective, just like we did in case of the central potential. Now before we do that, let me simplify this a little bit. Let us take mgl outside, or let me define my V effective theta prime as cos theta plus, here what I do is I divide everything by So here I can write I alpha. See, I have one I alpha here. I can take I alpha square common outside from the denominator bracket. So that gives me 1 I alpha. I can also take alpha square outside. So that gives me alpha square. And that half I keep here. And remember that I have already divided by everything by mgl. Then this term becomes 1. And this term becomes the ratio of I beta times beta and I alpha times alpha. So we define kappa as half I alpha alpha square by mgl. See, this quantity is dimensionless because what is I alpha alpha square? Let us look at it a little bit more closely. So we defined alpha here. So you see, this is an angular momentum which is I times alpha. So alpha is like angular velocity. So if I have I alpha alpha square by 2, that is like the kinetic energy because of the angular velocity. So that is what I have in the numerator of kappa. In the denominator also I have mg capital L, which is nothing but kind of this is numerator is kinetic energy. This is like the effective potential energy or the characteristic potential energy. Kappa is the ratio of these two. Similarly, I define gamma, which is beta I beta. See, beta I beta is like angular momentum. It's omega times I by alpha I alpha. So it's the angular momentum in the ratio of the angular momentum in two axes. And if I do that, I can now define V effective theta prime as, see how simple it becomes, cos theta plus kappa 1 minus gamma cos theta squared by sine square theta. So the energy is I think I alpha by 2, sorry. I should, okay. So I can rearrange this. What happens if I rearrange this? What I do is that I write E times 1 minus U square divided by mgl. What is this quantity? This is I alpha mgl by 2 u dot square plus everything I am multiplying by 1 minus u square, right? So I get u times 1 minus u square here plus kappa times 1 minus gamma u whole square here. So if you look at this, this kind of looks like a kinetic term and a potential term. Which it is, apart from the fact that I have to divide everything by 1 minus u square. Now obviously that has certain consequences, but let us not go into that. Let us look at this effective potential, which I don't like to write as V effective, but write as Fu. So it is this quantity that we want to look at. Now, what do you expect? Well, if this potential has a minima, so this potential as a function of u, if I plot, looks like this, then there is a stable fixed point, a stable equilibrium point, and if my energy is something like that, whatever you think of as energy, then the system will oscillate between these two ends. So it will not have a closed orbit, but it will have a bound orbit, right? So let us now investigate what happens for this. So for that, what I have done is, for different values of kappa and gamma, I have plotted this potential. So what I am showing here is that how this thing changes with gamma if I keep kappa equals 4. Remember, kappa was the ratio of the effective or characteristic kinetic energy with the characteristic potential energy. So I am just saying that there is more kinetic energy than the potential energy. And what was gamma? Gamma was the ratio of the angular momentum in the symmetry axis and perpendicular to the symmetry axis. What I am plotted here is cos theta along x, and cos theta along x so this is essentially u. This is essentially u. Theta equals to 0 is here. So that place corresponds to theta equals to 0, because x square cos theta is 1. And for different curves, I have different values of gamma. In y, I have plotted that f of u, which is the f of cos theta. What happens? If my gamma is 0.5, then I get this curve. So what is this curve? Well, this curve tells you that at theta equals to 0, this potential has a minimum. So if gamma is 0.5, it will always stay at theta equals to 0. And remember that theta equals to 0 is a vertical, so it will try to stay there. For all the other curves, you see that the potential has minima somewhere. And what is the consequence? Now imagine that I have a kinetic energy, I have a total energy which is this much. Then, if my gamma is given by this, then I have these two values of theta. So this is theta minimum and theta maximum. In between these two, the system will oscillate. If I have gamma to be larger, then the theta in between which the system oscillates is also larger. Okay, remember these things. Now let us see. Here we are looking at what happens if I vary kappa keeping gamma fixed. Vary gamma keeping kappa fixed. What happens if I do the other way? So what I am doing here is now have kept gamma equals to 4 and varying kappa. So remember, kappa more means we have more kinetic energy than potential energy. And this is the kinetic energy 1/10 of the potential energy. And you see, remember that this is theta equals to 0, and this is theta equals pi by 2, 90 degree. So you see that here it is maximum. So if kappa is very less, then the system will essentially roll down. It's not in a stable equilibrium. On the other hand, if kappa is greater, so like 1, 2, 3, 4 something, then if I start the system here, so if I give the enough energy and the configuration of the system there, then for say, okay, so I dismiss that curve, but anyway, so if the system starts, okay, so say the system starts here, then it will come back there and go up to there and then again come back. So it will oscillate between these 2 points. What kappa does is it provides the depth of the potential well. In the previous case, you remember what gamma does is provides what is the width of the potential well as well as where is the minimum. Okay, so keep these things in mind. So that's it. So what happens to this motion? Let us look at the symmetric top once more and see what is its motion. So that's my symmetric top. Remember, this angle is theta, and theta oscillates between two extremas. So you can think of these two lines. So theta will go back and forth between these two. This was psi, so there will be rotation in psi. And then there is a spin which is given by phi. If I look at the tip of this top, that will make a full circle in psi. The tip of this top, which is say this point, the center of the top, tip of the top. If I look down on xy plane, so say this is my x, this is my y, the tip of the top, which let us denote by red point, in the xy plane it will look like this. Well, not quite so, because you see it's not only doing this, the radius of this circle is fixed by the value of theta, which means it is just not going like this, it has to be bound between two radii. And so I should draw two circles which corresponds to, one corresponds to theta mean, the other corresponds to theta max, and the tip will move like this. It will never be a closed orbit, so it will continue like that. What else is happening to it? Well, that is the motion of the tip. If I now, instead of the point there, if I consider a point here, this is rotating with phi. So which means this is this point. Okay, so let me draw this red. So this curve should be the red curve, and on that red curve, around that red curve, this point rotates around. So I will get this motion. Okay. The motion in theta, which is the oscillation between these two, inner and outer, remember, is called nutation. The motion in psi, which is the fact that it goes around like this, is called spin. Is called precision, and the spin motion is self-explanatory. Okay, so I'll stop here, but consider the case when this top will suddenly topple. So what may happen is the following. So let me draw a top which looks a little different. Okay, so it has a pinpoint in the other end also. So you start its motion giving this, etc. And you will see there is enough YouTube video to demonstrate it, and I don't know whether you have done it in your childhood. We have done it many times. It goes upside down. It's called tippy top. So think about when that can happen. So that's it for today. We analyzed the motion of a symmetric top, and it turns out to be quite complicated, but we have some handle on it. That's all that we'll speak about Unit 3, which is rigid body motion. Thank you.